So yesterday we have talked about, so there is different couplings. The possible couplings are heteronuclear couplings and then homonuclear couplings. But out of that, we have ruled out something. So C13 is not going to couple with the C12 carbon. At the same time, C13 is also going to couple with the C13 because of its low abundance. Because of its low abundance. And so you can see only one thing, C13 can couple with the hydrogen. C13 can couple with the hydrogen. Homonuclear couplings are avoided and then only heteronuclear coupling. So if this coupling is observed fully, okay, if you are having a molecule like this, this is a natural product, very big molecule, you have a lot of hydrogens, you have a lot of carbons you have. So if you talk about these type of molecules, bigger molecules, when you take the coupled spectra, when you take the coupled spectra, that spectra looks like this, and you have that spectra looks like that, and this looks like very complicated. It's like very complicated, and then you cannot get much clear intuition from this. There will be a lot of overlappings, and you will not get exact signals where it is going to be occurred. And these things are there. And another one is, so this peak is very important. Yesterday I told CDCl3 peak is going to give us three triplet with same intensity. So it is a triplet. You are not able to see properly, but it is a triplet, and then it is giving same intensity peaks. So this peak is going to be the CDCl peak. Okay. So the coupling of the hydrogen with the carbon, the heteronuclear coupling, the coupling of the hydrogen with the carbon is going to complicate the spectrum. The protons are coupling because it is more complicated. Proton coupling with the second going to cause more complications in the C13 spectrum, more complications in the C13 spectrum. Okay, so that is what you can see here. To remove that complications, more complicated spectra, so you want to get a simplified spectra to get more information. So to do that, there are some, you have to do the decoupling. If it is coupled, you are getting more complicated spectra. So then you can do the decoupling. Decoupling means you are going to remove the coupling of the hydrogen. You are going to remove the coupling of the hydrogen. These decoupling methods are going to simplify your C13 spectra, and that is going to increase the intensity of your occurred signals. And a decoupler is used to remove spectra of the proton. Whenever you are using a decoupler, and that is going to remove the spin effect, whatever the spin effects are present for the proton, it is going to remove from the spectrum. So when it is removing, the spectra is going to be simplified. Without hydrogens, only carbons information you are going to get. So your spectra looks very simple and is analyzed very easily. So this is the, and how we are going to do this decoupling. A second reagent factor gets irradiated one hydrogen. This is our radio frequency. A second radio frequency we are going to generate, and that is going to irradiate with the hydrogen resonance. So when it is going to irradiate with the hydrogen resonance frequency, all the hydrogen nucleus are all the hydrogen nucleus will go into a saturation mode. Completely, they go into saturation mode. When it is there in the saturation mode, okay, the effective averaging all the spin states is going to be equal to zero. Saturation means all will be in same orientation and then same place. Everything is saturated and then they will be stable at that place. If you have all these things, that is going to equalize the zero. That is going to equalize zero. So this is the thing you can see here. So because of the second radiation frequency, what we will generate, and that radiation frequency should be there, and it should match with the hydrogen resonance frequency. If it is not matching with the hydrogen resonance frequency, the saturation will not be occurred for the hydrogen. So whatever the second generated radio frequency is there, and if you irradiate with that, that should match with the hydrogen frequency. Then the saturation of the hydrogen is going to come, and you are going to remove the information of the hydrogen, because when it is saturated, its spin states are going to be zero. All the averaging spin states are going to be zero. And there is a hydrogen channel. This is a hydrogen channel. So this is hydrogen channel. This is the pulse of hydrogen protons. All are at same level. You see upper and then lower. You see the energy is same, and then all the nucleus are in same. So average of this nucleus is going to be equal. So like this, a saturated state is going to come out when you irradiate with the radio frequency, which is going to be equal to the proton resonance frequency. And in that case, so other frequency will be there. That frequency it will excite the C13, and you will have a C13 pulse in this way. So when you are having C13 pulse this way, so Fourier transformation. So this is going to give the signals of your C13. This is going to give the signals of your C13 with a different pulse. So you are using two pulses. So first you are irradiating with the and pulse which irradiates C13 as well as hydrogen, and again you are irradiating with the hydrogen, and that will saturate the second generation, a second radio frequency, which is going to be equal to the hydrogens, and that saturates all the hydrogens like their state or some state, and they will be saturated. Their intensity is going to be equal. That means their averaging spin state are going to be equal to zero at that time. Okay, you will lose the proton, you will lose the proton string information. So that is what you can see here. So in that way you can decouple or you can remove the coupling effects of the hydrogen from the carbon. So this is one is decoupled spectra you can see, and so yeah, one is decoupled, another one is a coupled spectra. These are CH3, CH2. So you are going to have one, two, three, four signals. Four signal out of four. This is the third one. Okay, now to that is here one go. The first one should be this one, and second one should be this one, CH2 proton, and CH3 is going to be this one. So sorry, this is a fourth is going to be this one. So if you see this particular, this is a TMS, it is there. Okay, you forget about this. If you see this one, it is a having one, two, three, four, four. Intent, so multiplicity of this particular signal is quadrant. Four is there. So multiplicity of this particular one is quadrant. This is also four. And another one, this is triplet. So this is three, and this is a singlet, and without any hydrogens. So when you are having the hydrogens which is attached to the carbon, those carbons will come as the quadrant. So that means first one and then fourth one will be coming as the quadrant, and second one it is attached with only two hydrogens. So it is going to come as the triplet. Second is going to come as the triplet. So first one and fourth one is the quadrant, and second one is the triplet, and third one is going to be singlet. Okay. So here this is with the proton coupled. This is a proton coupled spectrum. And this is proton decoupling. So you are not having any effect of hydrogen. That means the basis which shows one hydrogen. That means here we are having a decoupling of the hydrogens. How many different carbons are there? We are having four different carbons. So you can get the four different carbon signals. This is second one, this is fourth one, and this is the first one. So you can see very clear spectra here only with the only one signal. There will be no multiplicity, there will be no deviation of the conventional lines. So like this is a simplest spectra. When you remove the hydrogen coupling, when you are going to decouple the effect of hydrogen, so that is going to be effect of the that is going to come as a that is going to come as a so singlets. When you are having this, so it is going to come as a like one is quadrant, another one is quadrant, and then one is plane. and this carbon is going to come as the signal. Okay, so this is the simplified spectra when you have the decoupling with the hydrogen. This is a differentiation between the coupling and the decoupling spectra. So if you see the large molecules, then you will understand the importance of coupling and then decoupling. So in the previous example, okay, it is not that much complicated. So decoupling spectra also it is not much complicated. You can have an imagination that so what is going to be happening there and then what is the things. So now you can see that. So when these all these carbons are having the coupling with the hydrogen. If you are having a hydrogen coupled spectra, you are going to see this type of spectra. It is a little bit complicated. But when it is having a decoupled, hydrogen decoupled spectrum, so all these multiplets are going to be a singlet and this is a CDCl signal and how many different carbons are appeared here, how many lines are there, that many different carbons are there in this particular ring. So this information will be very clear and then you will get very good information at this place. So when you are having decoupling, the simplification of the spectra. For this decoupling technique, in see that in decoupling techniques are very regular.